welcome back. It's Ashir here. So, this is the lecture 1, part 2. Previously, we talked about different types of agents and we gave a little bit of intro about environments, and we had lots of examples and tried to discuss everything, right? And in this lecture, I'm just going to talk about environments but in much greater detail. And the main goal is the same as the last one. You know, try to figure out what types of environments are there, all the different sets of environments, so we can build the best suitable in artificial agents for it, artificial intelligent agents for it. So, let's start. So the first, the very first um, environment that we have, or environment type that we have, is either fully observable or partially observable. Now, it's very obvious from the name that uh, there are environments that are fully observable, there are environments that are partially observable. But I would like to still explain with an example. Now, if you talk about fully observable environments, then we can take an example of chess, right? So in chess, we have the entire state of the game board, including all the position of all the pieces, right? So um, let's say if this is the chess board, right? Then I know where my enemy have um, their you know have their things at. I know where my stuff is at. I know all the position, I know all the states and everything, right? So this is fully observable. There's nothing hidden here. The Each and every state, each and every piece of this whole game is observable to me. So this is an example for chess. In a formal definition, we can say in a fully observable environment, the agent's sensors have complete access to the current state of the environment. The agent can directly observe or sense every single thing it needs to know about the world. So basically, it can sense or observe everything about the world. Okay. So, by the way, in this example, this chessboard is the world, right? So it can observe every single thing about it. Where are the pieces? Where are the enemy's pieces? Where are my pieces? Everything, right? Now you will better understand fully observable when I'll give you an example of partially observable. Now, an example for partially observable environment would be a game, some sort of card game, or more specific, um, it can be poker. It can be a game like Uno, um, something like that, right? Where you know what cards you have, but you do not know what cards my opponent has. So, poker or Uno is an example of partially observable environment. Each player holds private cards, and opponents do not have complete information about each other's hands. So you do not know about your enemy's cards, and your enemy doesn't know about yours. So this is a partially observable environment, right? In a much more formal definition, we can say that in a partially observable environment, the agent's sensors do not have access to the complete state of the environment. It has some information about the state, so some information may be hidden or uncertain, right? Do note the word uncertain here. because sometimes there might be cases where you have some idea about the whole world, but you are not 100% sure. You are uncertain about it. So that also comes under partially observable environment, right? So now the second thing would be uh, deterministic versus non-deterministic. This is again pretty basic. You can get a pretty good idea just by looking at the names. Deterministic environment is something uh, where you can determine the next state, where you can determine the next move, right? Non in non-deterministic states, you do not actually know about your next move, right? You are uncertain or you are not sure at all. So an example for a deterministic thing would be chess again. So chess under standard rules is deterministic. So if you know the current state of the board, if you know the current state of the board, like if you know all the pieces are like this, right? And if you know the move made by your enemy, right? Then the next state is entirely predictable. Like you can predict that, okay, the best move I can make is go here, or even this is possible, or even this is 100% uh, confirmed confirmed that if you move straight you will go straight, right? If you go straight with two moves, then you will go straight with two moves. If you move diagonally, then you will move diagonally. So it's fully deterministic, right? On the other hand, there are environments that are not very you know deterministic, right? So such environments have some level of unpredictability even with the same action in the same state. So I think I had given this example of self-driving car standing on a traffic signal, and I said that, let's say you pressed the accelerator, right? You took this action to go straight, but suddenly this pedestrian arrived. This pedestrian came in front of you. Now this action was basically, it didn't moved you to the state where you wanted to be. You wanted to go fully straight, but you cannot now. So you are at the same place where you were. So this is not deterministic, right? Different things can happen. Let's say if you wanted to go straight, but maybe your engine broke up, right? Maybe there was some problem with your tires. Maybe you wanted to go straight, but there was some problems with your tires and you drifted towards the right. So there's high probability that you will still go straight if you took this action to go straight, but it's not 100% sure. So it's non-deterministic, and this is basically what this means. So a very basic example, as I said, are self-driving cars. So many random things can happen in the real world, right? And another example can be this game called Ludo, if somebody has played it. So you play a move, but whoever plays a move, they roll a dice, they roll some dice, right? Now what moves is comes because of these dice is completely random, right? Maybe it's 6 and 2, maybe it's 1 and 1. It can be so many things, right? There are so many possibilities. So you are not 100% sure that what will be my next state here, right? So a Ludo example of Ludo is also non-deterministic. Okay, so this is it for the second type. Let's talk about the third type, which is episodic and sequential. Now things might become a little bit less obvious for you. What do you exactly mean by episodic and sequential, right? You might have some idea, but you will be a bit confused now. So episodic environments. Let's start with the definition, right? The agents in an episodic environment, the agent's experience is divided into independent episodes. Each episode is a self-contained sequence of actions, and the outcome of one episode does not affect subsequent episodes. Now, what does exactly that means? Let's take an example. Let's say we are playing tic-tac-toe, right? And each single move, or not each single move, but each game is a separate episode, right? So you played this game with your friend, and maybe you lost, right? You lost. Now this whole game will not affect the next game you and your friend will play, right? It is not affecting. So by the way, please do note that I'm talking about a completely new game. If it was if it was a new move in the game, let's say if I played this and your friend played this, then this is not episodic anymore, because you know which move you have played here, your previous move actually affects your whole journey, right? So this is something different. But if we talk about the whole game, right, you lost or won this game, it doesn't affect the next game, right? So what is sequential? Sequential is opposite of that. Very simple. In sequential environment, the agent's action have a long-term impact. In the current action sequence, consequence, sorry, affects future actions. So this is obvious that memory of past actions would be required in this case to make decisions, right? So a very again I'll repeat this example again, which is of chess. If you play a move, if it was a bad move, that will impact your game negatively. If it was a good move, it will impact your game positively. If it was a neutral move, then it will not impact your game at all, or maybe neutrally impact your game, right? So each move is contributing something, right? So when you are playing chess, you have to have some memory of your past actions, right? And maybe you had this clever trick in your mind that I will play this move and that, and then this move and then this move, and this way I will checkmate this enemy of mine. So you, for this whole trick thing, you still have to have memory, right? So chess played over multiple rounds is a sequential environment, right? The consequence of moves made in one round carry to the subsequent rounds, requiring the player to have a strategic memory. By the way, another way we can think about this is if you take an example of FIFA World Cup, right? So if you lose a game, let's say a team, let's say Brazil or Brazil had like 5 games, and it had to win 4 games to not get knocked out. But if it loses 2 games, right? If it has lost 2 games in past, then it has a consequence on its future, right? Now it is knocked out of the World Cup, it cannot play anymore. So this is a sequential environment as well. So let's move to the next type, which is static and dynamic. So let's start with very simple definitions. In a static environment, the environment remains unchanged while the agent is making decisions, or just thinking of moves, right? So there is no change in the environment during the decision making process. Please note, I'm only talking about decision making process here. I'm not saying that when an agent will make a move, then it will still be static. Obviously, it has changed, right? The agent has made a move. But when the agent is thinking, when the agent is trying to think of its next decision, nothing else is changing. Now you might be a bit confused. What do you mean? What are the examples of environments where when you are just thinking things might change? So that's dynamic environment, and I'll give you a really good example to understand this. But for static environments, an example could be again chess. And trust me, guys, I'm not obsessed with chess. So, but anyways, when you're thinking about your next move, your player cannot do anything, right? They have to wait for you. So the environment or the world of yours is not changing at all. It's static, nothing's changing. But let's say if an environment is like let's say real world, and you are basically a self-driving car, right? So even let's say again the same example, you are stopped at a traffic signal. Now you are not making any move right now, but you are actually you are in this decision making process, right? But the whole world is not like stopped for you. There might be pedestrians who are walking here and there might be other cars which are moving here and there is this engine of your car which is constantly running and has some probability of getting broke down. So many things are happening, right? It's not static. So this is an example for a dynamic environment. Let's move to the next point, which is discrete or continuous. Now, this is not the same as the last one. I have seen a lot of people get confused between these four things, but it's a bit different, and I'll try to explain. So, let's look at the formal definition of discrete environments, which is in a discrete environment, there is a limited number of distinct, very, very clearly defined percepts, states, or actions. The variable take on distinct values without continuous variation. Okay, that was quite complex, right? But I'll explain you with an example now. So if we take an example of tic-tac-toe and how it is a discrete environment, then you know that there are finite number of cells in the grid, right? There are how many? There are 9 cells, right? And there are very finite number of moves as well that you can take. So this is quite a discrete environment, right? So now what is an example for a continuous environment, or what is the definition for it? So in a continuous environment, the variables can take on lots of values, lots of like continuous values, continuous percepts, states, and actions, and they are not restricted to a distinct value. Like there are lots of options, like like not very well like you can say defined, like in this case. So an example for this might be a robotic arm. Now this might be a bit confusing, but I'll explain you. So when you're controlling a robotic arm, there are infinite angles that you can actually use it for, right? Like you can put it in infinite number of possible values, right? So it, you can have it in straight, you can have it a very 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 little bit curved, you can have it a little bit more, and there is like very, like, extreme amount of possibilities. Like it's just not possible to count, or say it's finite. So there is this continuous environment now, where you can put it in so many angles, nearly which are infinite. So this would be an example of a continuous environment, which is robotic arm in a controlling a robotic arm in a factory, right? So now let's talk about the last one, which is single agent and multi-agent. Okay, so a single agent environment just means there is only one agent operating by itself in the environment. That's it. So the actions and decisions of this agent do not directly influence other agents. A very simple example would be, let's say there is a maze, right? Let's say there is a maze and these are walls in it, and you have to go from the starting point to this goal point. Now if you are a robot, you are just a single agent, right? Like your decisions are not affecting any other agent, and any other agents are not affecting your decisions here. So you just go here and you are the single agent, you are in a single agent environment. But um, a multi-agent environment can be something like there are multiple agents operating concurrently, and the actions of one agent can impact the state or decisions of other agents. Now I'll give you some uh, cool example for this. Let's say we have another grid where two agents, there is this agent 1 and then there is this agent 2, and then we have these walls, let's say, which is like this, and the goal is here. All right, so now what will happen? Let's say this agent and this agent can now communicate with each other, right? So what will happen is this agent will, let's say, move to the left, and it will say, it will communicate to this agent that in this specific position there is a wall, so do not take this path. Now it will not take this path because it knows it has a wall, so it won't waste these moves. Then it will do the same about here, 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 right? So they can work together to reach this goal state. So this is a multi-agent environment, right? Another example of this could be playing an online multiplayer game, which involves a multi-agent environment, right? Maybe you are playing PUBG or Fortnite with your friends. So maybe instead of you and your friends playing, there can be 2 or 3 or 4 artificial intelligent agents playing that game, right? So the actions of one player will affect the actions of another player, right? Or maybe it will affect the experience of each other in that game world. So yeah, there we go. Now let's talk a little bit about um, you know um, how do we, like, why do we even care, right? So think about this. um, we have to, like, be extremely careful when designing our agents about which specific environment type is you know is our world is. Let's say if I'm designing an agent for Pac-Man, then I need to know that I know that then my environment is fully observable. My environment is maybe um, deterministic. It is maybe sequential. It is dynamic. It is dynamic because there are enemies there which are moving to catch you, so things are changing. It's discrete. There are very finite number of moves you can play, and it is also uh, maybe single agent, right? So that thing, or maybe a multiple agent if you also take in account that the enemies are trying to kill you. So you have to actually know your environment before you design your agent, um, right? But the main question is, let's say if I'm designing for a self-driving car, then what is real world, then what type of environment is a real world, right? So always remember that in real world, um, things are partially observable. Things are partially observable. You cannot observe the whole world, right? The whole earth. That's impossible. It's non-deterministic. There are so many random things happening. It's sequential. Every single step that you will take will affect your whole journey, right? And maybe the next step and stuff. It's dynamic, which is super clear that everything's changing all the time. It's continuous because there are like infinite amount of things you can or path you can take. Let's say if I want to go from A till B, right? And there can be infinite many paths. Some might be extremely long, some might be extremely inefficient, but still there are like unlimited paths to this problem, right? So it's continuous, right? And one more thing is it's multi-agent. So um, it's actually like um, you know there are pedestrians that are affecting your experience of the game, and other all the other things like traffic signal. That traffic signals also affect your game. So in an example of Pac-Man, when we had these enemies, so we will now be a multi-agent because these enemies are also affecting what moves we will make. If I was going straight and these enemies are coming from here, then obviously I won't go straight. Now I will move left or right or go back. So these are multi-agent examples, right? Multi-agent environments. So that is it about the environments. I told you about the real world as well. So yeah. Now there's one last thing that I'll teach, and it's very super simple, and it's this thing called PEAS activity. Okay, so let's talk about it a little bit. So this basically stands for P stands for performance measure, and I also go into the reason why we do this. So this stands for performance measures. E stands for environment. A stands for actuators. I'll also explain what are actuators, don't worry. And then S stands for sensors. So the reason for doing this activity is whenever we are trying to create an artificial agent, we have to get these four things right. Like we have to define values for these four things before designing any artificial intelligent agent. And the reason is basically like let's say in the example of an self-driving taxi, right? You have to define performance measures in terms of safety. You have to tell your self-driving car that you have to drive safely. You also have to tell that performance measure is also whether you are reaching the destination or not, right? And it's a taxi business, so another performance measure is how much profits you are making. Another thing can be comfort of the taxi, how comfortable is your taxi. So these are all performance measures measures, right? Performance measures. So then we have environments, right? Now in terms of this self-driving taxi, you can describe your environment like I will be driving on roads, and I will be driving where there would be other vehicles, so there would be traffic in the environment. There can also be pedestrians, so people can come and go. So this might affect how I'm actually driving the car. So stuff like that. And then we have this thing called actuators. Now actuators, I'll give you example and you will understand what actuators are. Actuator in this self-driving taxi thing can be steering, can be accelerator, can be a brake, can be a speaker, right? So you need a steering wheel. So right, you need an accelerator to accelerate. You need this brake, this physical brake. You need this physical accelerator. You need this um, steering wheel. So stuff like that. If we talk about a robot, let's say a walking robot, and I ask you what are its actuators, then you can say okay, it needs to walk, right? So it will have these walking legs, right? So you know um, stuff like that basically. uh, that's an actuator. Now just what parts should be there. So the fourth and final thing which is in this thing is S, which is sensors. That's pretty obvious. Sensors means maybe in this self-driving thing, self-driving taxi, the sensors can be a video sensor, which is actually using image detection to detect is there any car in front of me, or in the back side, or on the right of mine, or on the left of mine, is there any person anywhere. There can be engine sensors which can measure what is the status and performance of the vehicle. And there can be also a GPS sensor which is providing location and navigation information. So many things, right? So many things can be in there in terms of sensors. But now that I have described all of this by doing this PEAS activity, now I have a good amount of idea what are the things that I need to take in account when designing my agent, right? So when you say that your environment must be changing so much, you will say okay, then I need an agent which is not only goal based, which is not just utility based, but it should also learn. It should be a learning agent, right? It should learn about things instantly. um, so stuff like that, right? um, you first take these things out, and all these information, and then you just basically um, create your agent, right? So this is it for today. We are done with our whole lecture one, which was on agent and involvements. Please let me know if I'm teaching good, where should I improve. And thank you so much for putting in your time and watching my lectures. So see you next time. Thank you. Bye bye. Take care.